is one of design results. Design result. If you see here, calculate D in this case. Calculate D in this case using, as I explained, a input. So this is a step 1 calculation. Step 1, you calculate reverse outputs. The outputs that were moved to outputs which are supposed to be placed in input, because you want to preassign some of the parameters in reverse way. Do you follow me? This is something that I say as a reverse input parameters, right? So there you have to move some of the output that's supposed to be in input to outputs, right? So that we call that kind of output as reverse output. Okay, and D is one of the reverse outputs here, if you see over there. And we use a 100,000 big data. We generate 100,000 big data from the software based on ACI 318.14. I'll get there soon. And here we use a 5 layers, and we use a 40 neurons. Incredible. We have a 40 neurons. 40 neurons means we have a 40 circles vertically to try to form a artificial neural networks. And also we set a 50,000 epoch. That means that I want to go 50,000 epoch because I don't know how many epoch I'm gonna need to get a correct weights and biases. And the neural networks found that the best epoch for training, which means that the best epoch gave you the correct bias and correct weights. So this is now 15,095, and you're stopping a 15,595. The reason you go a little longer is that even though you got a best epoch right there, and the training continues to see if you can go and get better training result than this here. But at 15,595 epoch, you will stop. Because there is enough evidences that you cannot improve your training accuracies anymore. So that your neural networks stops right there at 15,595, and this is very lengthy process, and we have a mean squared errors, and this is also test squared errors and networks. I mean, see, the untest data are not seen by the artificial neural networks, and also come up with pretty small mean square errors, and the R value, the regression value, come out to be 0.988, which is very good. So this is how you interpret the accuracies and the design training results. Training edge is incredible. The training edge, you need to go all the way to 43,994 epoch for best training results, and it stopped at 44,994 epochs, whereas you are requesting 50,000 epoch for entire training processes. And this is probably because you're having a very complicated relationships of edge among all big data sets. And this is even more incredible here. If you train raw RT, you're epoch that you request in the beginning is not enough because you went all the way to 50,000 and 50,000, so that we're not sure whether we have achieved the best training results for ROLT with the required epoch of 50,000. So that it is always good to see your best epoch and stopping epoch before the required epoch. If you training ROLT even more dramatic because you went all the way to 50,000 for best epoch and stopped epoch is also 50,000, whereas your required epoch is 50,000 as well. In that case, we're not sure whether we have achieved the best epoch because you cannot go beyond the 50,000 because 50,000 is limited by the system. So that in this case, you want to go more than 50,000 to verify that you're having a best epoch always. But in this case, we didn't do that because the training mean squared errors and test mean squared errors are small enough to get a good designs, because this is -6, whereas you have a -5. So this is very nice, very good training results compared to this one where you're training output edge. However, you have reached 19,237 epoch when you are training ROLC. And also you stopped at 19,737, whereas you are requesting 50,000 epoch to train ROLC. So that you have achieved enough train accuracies because your epoch stops well before 50,000s, which are requested by the systems. And this is very nice to see these values, these epochs, which are less than the one that you requesting the training process to continue and terminates. One of the important thing here is the sequence of your training outputs. Here we train D and H and ROLT and ROLC right here. Okay, now the sequence of training outputs is very important in these trainings. Like you see over here, when you train D first, the D is used here to train H, and after you train H, D and H used here to train ROLT, and after you train ROLT, all these three parameters also are used as a input parameters to train ROLC. So the reason this is possible is that when you train D, you have all the output parameter together. For example, when you train D, you have also H, ROLT, ROLC in output parameter at the same time. So that when you train D, you cannot use these parameters as input parameters to train D because all the parameters are right now placed in output side simultaneously. But after you train D is released from output parameters. So D can be placed in input side to train H. And after you train H, D and H can be placed in input side for training ROLT and so on and so forth. So that it is good when you have a very complex relationship among big data sets for ROLC, because you can use all input parameters as many as 12. Now you are able to include all the pre-trained parameters in input side to train ROLC. You think ROLC is very complex relationship among big data sets. So this is very good way to train your parameter in sequence so that you can have a better training results. So you can put the most complex training parameters at the end while having all the training parameters on input side. And we define this sequence as TS1 sequence. Next one, we will take a look at TS2 sequence, where we're going to go train row RC first, row RT, and H and D, and try to compare both training result and design results based on these two different sequences. Which one is better for design of this type of reinforced concrete beams? And we're going to start with a row RC, and we have to have only 9 because we are having all the other parameters as a output parameters with the row RC. And after you training row RC, you can put them in the input side here to train row RT. After you train row RT, you can put row RC, row RT both in input side to train H, and then you go put everything here, make a 12 input parameters to train output D. And this is one way you can train all this reverse output. Okay, we are now training reverse outputs. And also the epochs are very small when you have best epoch at 9,519, only 10,000, while you are requesting the trend to go 50,000. Here less than 50,000, which is fine to me. And this is not less. This is some kind of ambiguous situation where we now really sure whether you have enough training accuracies were achieved or not with the output H, because the training epoch, stopping epoch, best epoch are the same as the training, the required epoch, which is 50,000, and here same here. Okay, but we did not extend 50,000. We thought that the training accuracies that we have achieved were sufficient enough, so we didn't extend it. But you better have the established or required epochs always greater than the one that you have best epoch here and here and here. So this is very important to understand. Okay. Now in next clip, we're going to compare the design accuracies between TS1 and TS2, and this gives you an idea when you have a less design accuracies that you want, then you can change the training sequence, as you see over here, to try to enhance your training accuracies, leading to design accuracies, the better design accuracies.